Thank you, Hussein. And as being the second lecture, I should start by asking if there are questions about the first one that people thinking through last night in the silence of the desert. I'll use that going once, going twice. Okay, so just kind of a brief recap. So yesterday I kind of spent a lot of time emphasizing how isolated quantum systems thermalize. That's kind of like a generic feature that we expect if you have a strongly interacting system. And I kind of ended up by showing you that if you have an ability of kind of like halting thermalization, that you can use it to effectively see out of equilibrium phenomena that last as long as your system fails to thermalize. And if we believe that the MBL phase lives arbitrarily long, that gives us an arbitrarily long, robust phase of matter that is outside the scope of kind of like the way that we think of phase of matter in a symmetry breaking regime. So today I kind of want to, sorry, it seems like there's some oscillation. Okay, so today I kind of want to continue that thread and kind of talk about two other kinds of out of equilibrium phenomena. One, which is going to be this Foucault prethermalization, where I'll hopefully teach you how we can use a drive to engineer interesting phenomena and kind of manipulate the thermalization rate of an isolated quantum system. And then I'll end up on kind of like going more on these two topics and kind of comment on how the addition of novel conserved quantities can fundamentally alter the approach to equilibrium. In this case, giving the rise to kind of like anomalous form of hydrodynamics. So that's going to be the plan for today. And my third lecture is going to be on something very different. There's a question in the back. Yeah, so Lieb-Robinson bounds. So Lieb-Robinson bounds are kind of a fundamental speed limit on which a quantum system can exhibit. What you find if you do like a disorder experiment is that the amount that information propagates is going to be much slower. In particular, in these MBL systems tends to grow with the logarithmic of times rather than the polynomial. Because the speed is like it goes with a logarithmic of it has a logarithmic light count, meaning that it goes very, very slowly, rather than linear or diffusively. So there are some connections. I won't make them. There is maybe a point where I can comment a little bit on how those enters in the story of prethermalization, but we should chat afterwards. Awesome. Any other questions about the goal? So in this lecture, as I said, there's going to be two topics. One is going to be this prethermalization. And I'll kind of tell you how we can slow down thermalization by using a drive. I'll focus in driven systems, kind of allude to the fact that this is actually a generic feature. I will kind of comment that this is kind of an approach that we can use in all isolated quantum systems. And I'll kind of build a new kind of discrete time crystal that is different from the one I presented before. And I'll make some comparisons and contrast between the two. And finally, I'll talk not about dynamics away from equilibrium, but dynamics near equilibrium, which is how we understand kind of the motion and the propagation of conserved quantities, and how that can affect some interesting observables in our system. In particular, how we, in kind of like in hydrodynamic, an integral model, we can see something that looks like Carter-Parisi-Zhang universality, but it's not quite that. Okay? So prethermalization, slowing down thermalization. So one of the questions that we came across yesterday was the idea that if I start with an initial state and I let the system evolve under my dynamics, eventually it approach a thermal state with respect to some Hamiltonian. Yeah. And this was one of the things that we were thinking about in terms of quantifying the equilibration. But the other question that we were asking was exactly what is the time scale on which this happens. And that time scale itself also affects our understanding of the dynamics of these isolated quantum systems. So in general, this is a very complicated question that depends on the details of the Hamiltonian that generates the dynamics. But today I kind of want to zoom in on a particular class of dynamics, i.e. periodically driven or Foucault dynamics, where we have a time periodic drive. Okay? And in this case, as I kind of like commented yesterday, we expect that the final thermalization, the final thermal state is the fully mixed state, just corresponding to the identity. Yeah. So one way to envision this that I think will be very helpful as we think about the physics of this model is that we have, for example, a spin system. And what this periodic drive is doing is that even though the dynamics are fully conservative, there's no entanglement being formed with the outside, effectively the system is being driven at some frequency omega, which is effectively given by the inverse of this period of the drive. So this, let me also note that the systems might interact with one another, and that's going to happen at an energy scale that I'll assume is going to be J. So the important aspect that I think this drawing is alluding to and that I want to emphasize is at the moment that we introduce a drive, we implicitly introduce a new energy scale on the problem, in this case given by the frequency omega of the drive. And that new energy scale is going to be very important for the dynamics because we expect that the way the system heats up to this infinite temperature state is fundamentally dictated by the way it absorbs energy from this drive. There's going to be the interface between this omega and J that's going to lead us to understand the thermalization timescales and the thermalization dynamics. Okay? And so at late times, you expect that whatever these initial configurations spin, it's going to be very disordered, and that's fundamentally given by this drive. Okay? Now, the regime I want to focus on for today is the regime where my frequency on my drive is much, much larger than my local energy scale J. Okay? And if you want kind of a mental model for the absurd limit of this is you're shining your laser into a swing. The swing has a Hertz scale frequency. Your laser is going to be terahertz. And so you know that you're driving your system with a very fast drive. And it's not like your laser is going to bring that swing fast to equilibration, right? So that's kind of like, and that example also tells us that we expect that this thermalization timescale is going to be very long. Okay? Now, there's a very simple way of understanding that's going to allow us to actually make a very precise expectation about this, which is that if you have a very large energy scale on which you're trying to drive the system, if the system's trying to absorb a quantum of energy from the drive, it has to undergo a lot of local rearrangements. If I'm trying to absorb omega, I need to do, for example, like 3 spin flips so that the energy scale, the energy change of the interaction of the interactions between the spins is able to accommodate that additional h bar omega. Okay, and as I increase my frequency, I'm going to need more and more local rearrangements, which are a very off-resonant process. You can actually kind of like, you can actually from this kind of get an intuition that the rate on which this energy absorption goes is very much going to be given by a process in perturbation theory that's going to be of order omega over J in process in perturbation theory. And if you take this at face value, you then should expect that the rate of heating is going to be exponentially suppressed, is going to have some energy scale, some constant, but is going to be exponentially suppressed by how many layers of perturbation theory I need to do. And that tells me that I expect that this heating time scale should actually go as e to the omega over J. Okay? So this is what I mean by having a way of controlling the thermalization scale of my system, because if I can only manipulate the period of my drive, I suddenly can open up an exponentially large window of time before the system thermalizes. Okay. So is this intuition of local rearrangements clear? Going once. Okay. So this is going to be the basis of the talk. So I really want this. It turns out it doesn't matter. So that's a very good question. So I kind of define this J as kind of the local energy scale. So if you have nearest neighbor interaction, this is basically given by J1. But you can imagine that if you have a longer range term, it should effectively be like the sum of all your coupling constants. One way to broadly think about this is that this J is kind of like a measure of how much energy do you change if you do a local flip. And you can imagine that the order of perturbation theory that you need to go is going to be on each spin you do the maximal change, and that's going to set how many local processes you need to go, which sets the order of perturbation theory, which sets this exponent. Does that kind of answer? Perfect. So this is kind of cool. It also tells us that we have a very weird problem, right? Because if we think of kind of the time scale of the dynamics, I start my system with in some initial state, and there's going to be an arrow of time over here, right? And just to make it harder, make it easier to see, I'm going to write things in terms of the logarithmic of time. And you know that things are going to be weird once you do the logarithmic of a time. But what I told you is that there's a very long time scale over here that's exponentially controlled by this frequency, after which my system is effectively going to approach kind of like the fully mixed thermal state. Okay. Of course, my system is also undergoing some local dynamics. So expect that there's a time scale associated with 1 over j, maybe even n over j, on which the system approaches maybe some sort of local equilibrium, and then something else, right? But the big question is going to be is like, now I've created this big chasm where it's not a priori obvious what is going under the hood and what is the system doing, okay? And for that, I kind of want to give you a little bit of a machinery and kind of like an understanding of the properties of these fast-driven periodic systems. And so to do that, let me kind of go back to this and try to give you not a proof, but kind of a sketch of exactly how one gets to derive formulas of this kind. Okay? So the key idea is that we want to understand the dynamics of observables. And if I tell you that there is an exponentially long time scale, it means that local observables in some sense need to change very, very slowly. There has to be some property of the system that is maintained for a very long time. And if that property keeps fixed, I know that the system cannot thermalize because this initial state can exhibit with respect to that operator O, some value that is very different from the thermal state. So let's call this O0. At late times, I have an O of equilibrium. And if I have a difference in delta O, which I'll call O0 minus O equilibrium, if I know that O doesn't change very much, then that gives me an estimate of how long it takes my system to equilibrate because I need to overcome this amount of change in my operator. It turns out that the object that you look for is some sort of energy. So the point of the way that these proofs go to show that you indeed have this object is that you demonstrate that the energy density of the system doesn't change very much. And we can kind of understand why that is. And so to use that, let me kind of use an example where I pick a particular kind of drive, where I effectively evolve my system under some Hamiltonian H1 for some time that's going to be half of my period. And then I evolve my system under some other Hamiltonian for the other half of my period. This is kind of analogous to the picture that I drew yesterday, where I have some time, and my Hamiltonian effectively is like some step function that is periodic in time. Okay. So it turns out that if you have this kind of dynamics, and this is why it's going to be, this is why we think about it, it's very easy to compute the unitary that generates my dynamics, right? Because it's just being generated by two static processes, some H1 T over 2, and then I evolve my system for H2 T over 2, right? And the crucial thing is that if my T is very small or my frequency is very large, we expect that we can do some Baker-Campbell-Hausdorff and kind of collect everything into a single exponent. And this is where I need to kind of make sure that I use my notes to get the factors right. in principle, you can use Baker-Campbell-Hausdorff to turn these two exponents into one, and you get something that effectively looks like this. It's going to be h1 plus h2 over 2. And then the next term is going to be something that depends on the commutator of these two Hamiltonians. And then it's going to be weighted by time and some. And then they're higher and higher order terms. Okay. This kind of already tells us, this in some sense gives us a new evolution, which I'll call ITH effective, that in principle could tell us that our system could generate the dynamics of our system. Okay. So one thing to note, and this is kind of like why this kind of like in understanding of J versus omega is good, you can see that to zeroth order, you just get the average of the dynamics. And to higher order, you get the term that's then gets suppressed by T. And if the local energy scale is J, this is just the original Hamiltonian, and then it's going to be suppressed by orders of J times T. Okay. So what I'm saying is that if this Baker-Campbell-Hausdorff kind of converge well, in principle, we could say that the full dynamics of my system are actually approximately generated by an effective static Hamiltonian. Okay. Crucially, we know that this is not exactly right. There has to be a little bit of an error. And the crucial thing is that this error is kind of bounded by some term that goes exponentially in the frequency. Okay. But broadly, this is kind of nice, because it tells me now that I can understand my dynamics by comparing the full evolution that I've been calling U and UF interchangeably against the dynamics under this approximate unitary, which is just generated by this object. Okay. And then if we understand the dynamics of this particular observable, it isn't a good observable like magnetization and whatnot. I can understand its dynamics if I do the total evolution, which is going to be something like this on my system. So this is how much, this is effectively my effective energy after a period T. I can compare that with respect to my effective energy after evolving by this approximate Hamiltonian. And I'll call this H effective tilde. Right? Yeah. No, it turns out that you need this I because these are two emission. So if you think of like sigma x, sigma z, the commutator of that is I sigma y. So it turns out that this is still an Hermitian object. So you don't have weirdness of that. So this is still like an I times a Hermitian object. That's the I that you're worried about, or was it this particular I? Okay, perfect. So the crucial thing about choosing this particular operator to understand the thermalization is that because H effective is generating the dynamics, I know that this has to be the energy at times equals 0. So this tells me that if I look at the dynamics under my under my total evolution, it might change a little bit. But if I do after my approximate evolution, it doesn't change at all. And because this error is small, you can actually show precisely that the amount of energy that gets affected, that gets changed, turns out that you should use energy density. I'm kind of going to gloss over that fact for a moment. The amount of change of your effective energy density is exponentially small. There should also be an N over here. Okay. Yes. It depends on time because here I'm assuming a period. So it implicitly is doing the. That's the approximation. Sorry, UF is the precise one. Yeah, sorry. So I'm using UF to be the precise evolution, and U approximate to be the one that effectively ignores these errors. Does that answer the question? Awesome. Any other question? Okay, so this is actually a quite generic result that, again, works for systems with long-range interactions, even like systems that, as long as you have a local notion of energy scale that allows you to tackle this kind of perturbative analysis, you can do something of this kind. And this is what sets the statement about this long thermalization timescale. Because if at every period, at most, you can change by a little bit of energy, it will take you an exponentially number of periods to change your initial energy density to the energy density of your fully mixed state. Okay? Okay, so this kind of tells you that, this kind of tells us, if we're able to kind of like recycle this guy, that's the advantage of doing it on the iPad, is that within this regime, I haven't told you what the precise dynamics are, but what I told you is that if I look at my effective energy, it effectively stays constant up until this exponentially late time, at which the system then starts heating up and approaches the infinite temperature state. Okay? Now, it turns out that this is a stronger claim, and you can actually show, and this I'm gonna, it's a little bit, it's more technical, so let me not go into those details, but it connects to the question of the Lee-Robinson bounds, which is if you look at the dynamics under this approximate Hamiltonian for many periods, sorry, this is an ugly expression, but hopefully it'll become clear. So let me first write it down and then I'll explain it. Okay. So what I'm writing here is two things, which is the dynamics of an operator. If I look at the approximate dynamics of that operator after n periods, compared with the precise dynamics of that operator under the same amount of time. And it turns out that you can, because of the approximate, how good this approximation is, you can actually show that that is still, we got some friends? Let me go back. Awesome. You can show that that is exponentially suppressed by this power. And then there's actually a power law factor in front. And this connects to the question in the back about Lee-Robinson bounds. So it turns out that the amount of errors that you make and the locality of your system matter a lot. If you have a system that is local, and this connects to kind of like Harry's perspective, I have a local error, and the more errors I have, they all stay local. So if I mess up a little bit of the operator at the start, all of my errors are still going to be somewhat localized. If I have a very non-local term and non-local dynamics, and I make a little bit of a mistake, that mistake can very fast propagate through my system where more errors can happen. So this kind of polynomial factor actually encodes how good your Lee-Robinson bound is, and it connects with notions of the locality of your Hamiltonian. So, but the point that I want to emphasize here is that as long as we have these notions of Lee-Robinson bounds, and we know that our system has some local dynamics, this notion of the system having a conserved quantity kind of gets elevated into the fact that this effective Hamiltonian is actually the generator of the dynamics. So that would take me on a big detour. The simple answer is the following. In relative, like when you think of like relativity, it tells you that two parts of the universe can't talk to each other because the speed of light is finite, right? the question of Lie-Robinson bound is trying to quantify that for a quantum system. I have a large metal rod, and if I hit it on the left side, it takes some time for information to propagate to the right side. It turns out that you can make precise statements of how fast information gets propagated, and those are known as Lie-Robinson bounds that set kind of like an effective light cone for generic quantum dynamics. It is system dependent. Usually they're just bounds that depends on the locality and the geometry of your system. The crucial thing is that if you have a system with nearest neighbor interactions, you have a sharp light cone beyond which all correlations decay exponentially. So I could go, if you're interested about this, I have a lot to say in the break, but I wanted to focus on other things for today's lecture. Any other questions? Awesome. So what I hopefully convince you very briefly is that the dynamics of the system up until this point is actually described as if I'm just evolving my system under this effective Hamiltonian. And then because I accumulate the small amount of errors, eventually at some time scale, at some very large time scale, those errors start accumulate and my systems start deviating from the evolution of it. Okay. So that's cool. We now have developed a very long way of understanding the dynamics over an exponentially large time scale, which is you usually don't get to do. But we can actually go a little bit further, right? So if in fact this effective Hamiltonian is equilibrating, we actually expect that the system is gonna not necessarily exhibit some very coherent evolution, but eventually it actually approach a thermal state that is given by this effective Hamiltonian. Okay, and maybe I can call this tau pre. And this is why it's called prethermalization, because I started a system where the thermal state that eventually will go to is a particular state, in this case, the fully mixed state. But I've now created the conditions for the system to inhabit in a different thermal state, a pre-thermal state, on which it approaches an equilibrium state, but that is completely different from the final state that it approaches. Okay. And now, in principle, I want to show you that this is true. And these are some numerics displaying this fact. So let me kind of like run through a little bit what we're seeing, because this is going to be helpful in understanding the later points. So I'm plotting the dynamics of a spin system that I'm effectively has some interactions between the different degrees of freedom. Turns out those details don't matter for the broad statements that I'll make. It matters like the coefficients. And then I'm driving the system by basically toggling on and off, or kind of up and down, the local magnetic field in a global fashion. So as I alluded to, the fact that I'm kind of like toggling the magnetic field means that the system's going to heat up. And I'm plotting two things. I'm plotting kind of like the effective energy of my system and seeing how the system changes this approximate conserved quantity. And I'm also looking at the entanglement entropy of my system. Okay. This is a measure that is independent of any observable, but it tells us stuff about the thermalization dynamics. Okay. So if we focus on the top one, what we see is that the system basically displays a constant energy density up until eventually in this log plot, it starts heating up and approaches infinite temperature value that in this case is going to be 0. Okay. The crucial aspect is I changed my frequency from 6 in units of 1/j to 7. And suddenly this increased by a factor of 5, the time it took my system to equilibrate. And I do one extra unit of frequency and I get another factor of 5. And then I do another unit and get a factor of 5. So this is exactly the statement that I told you, that the thermalization timescale of my system increased exponentially in the frequency of my drive. But it doesn't tell me exactly what is happening under the hood, and that's why it's good to look at the entanglement entropy. So at the start, we're considering a system that is in a pure state. So that's going to be this point. And what we're seeing is that under the dynamics, under this effective Hamiltonian, correlation is going to be formed between the left and the right. And this is kind of building up on what Christian told us. But eventually it's going to stop. And it stops at a plateau that's not exactly around here. It's about here, right? The system kind of approaches a plateau. And that plateau corresponds to the entanglement entropy with respect to this density, the thermal density matrix with respect to this effective Hamiltonian. You can actually try to compute that independently, and you see that there's agreements between them. And in principle, as I increase the frequency of my drive, my system lives in this prethermal state for longer and longer until it eventually heats up at a time scale that matches the time it heats up in terms of the energy density. So indeed, we see that I start from a pure state, I go to something that equilibrates, and then I go to a different equilibrium, which is the final equilibrium state of my system. Okay. And this is cool, but it's also very boring, because I just told you, I went through this entire song and dance to tell you how to take a static system, perhaps, drive it, mimic a different static system that eventually is gonna do something completely boring, which is go to the fully mixed state. So now I want to tell you that actually there's a lot of structure that you gain once you start driving a system, and that allows us to see phenomena that in principle you wouldn't be able to see in other settings. Okay. So I want to kind of like pose this as a thing. Can we go beyond effective equilibrium dynamics? Yes. So in this case, it's because my effective Hamiltonian is traceless, and so my late time thermal state is just going to be the identity. So it just measures the effective Hamiltonian, and this is always 0. And this means actually that if I start with a system that has positive effective energy density, it heats up by losing energy, because in that case, it has to also go down to this value. So actually, you get to play with like technically negative temperature states. I will always use heat up as go to the infinite, to the fully mixed state. But if it's not clear, please stop. This slope. So you should think that from this picture, you should think that, sorry, from this particular statement, you should think that every amount, if you look in a lin-lin plot, it looks like it's linear. So every period you heat up a little bit, and that is exponentially small. So the heating dynamics look something, if you look at the plot of the effective energy, it effectively looks like the zero energy, let's call it E0, plus some rate times the number of periods. And this rate is the thing that's exponentially small in omega over J. It turns out that because the rate is changing exponentially, it's much cleaner to see in a log time plot. Because otherwise you just see like one curve and then the other ones are flat. And then you're like, what is happening? Yeah. Yes. So there's a very simple intuition for why you should look at the energy density rather than energy, which is the amount of errors that you make are extensive, because you have a big system and you're driving and you're trying to do an approximation. So the amount of errors that you do are extensive. So the amount of the change has to be extensive, but the amount of errors per amount of system, that becomes like a well-defined property that has this. So maybe let me make a note that and system size. Awesome. Any other questions? Okay. So what I want to convince you at the end of this is that yes, and I'll show you some examples of what we can do. Okay. And it turns out that things get funkier if you play a little bit with the types of drives that you consider. So I'm going to do a kind of drive that's going to be reminiscent to what I did yesterday, which I assume that effectively I'm going to, let me write it in a different way. So I am assuming that I have some Hamiltonian that I care about simulating. And then I'm going to do this for some time t1. And then I'm going to do a rotation where I effectively apply a global field on all my spins. But I'm going to choose this such that it only lasts for a time, which is pi over g. pi over 2g. Okay. And the reason why I choose this should be h of t, is that once again, my dynamics are going to be very simple to analyze. If I compute it, it's going to be first I evolve under this effective Hamiltonian for some time t1. And then I'm basically going to do a rotation, which is minus I pi over 2 sum over sigma xi. Okay. And you should kind of like see that this is nothing but a pi pulse, which is proportional to doing a spin flip on every object. And for simplicity of the next few things, I'll just call this x. Okay. So this I'm gonna call x e to the minus I h t. Okay. So it's a particular kind of drive. It's not necessarily super generic. But it turns out that if your dynamics are of this form, you actually can, the effective Hamiltonian that you get has actually special properties. And we can understand this not by looking at the dynamics under one period, but looking at the dynamics under 2 periods. So we're going to do a little bit of algebra, but if we look at UF squared, this is going to be x e to the minus I h t, x e to the minus I h t, right? And because this pi pulse, x squared is going to be identity, or x dagger equals x. So I can actually bring this up and just call this e to the minus x h x t, e to the minus I h t. Okay? And now I can do my similar trick as before, and you get an effective Hamiltonian that to 0th order is effectively going to be x h x plus h divided by 2. Okay. And this is kind of seems innocuous, but it's actually kind of interesting because I didn't make any assumption about x, about the h that I put in here, right? But this effective Hamiltonian has the property that h effective x equals 0. Okay. So I drew my system, and now I actually suddenly found the symmetry. So suddenly I have a drive that took my generic Hamiltonian and did something to it, and now I have a new symmetry with which to play. And that symmetry is only guaranteed by the fact that I'm doing this periodic drive. Okay? So there's a couple of things. So let me give a different intuition about this, which is just that of spin echo. When you're doing spin echo in an experiment, you have a little bit of field, and you kind of like do a pi pulse to make sure that that field kind of like changes sign, and that is the way that you cancel. The crucial thing here is that because you're doing this in an isolated quantum system, your spin echo works exponentially well. So let me make that a little bit sharper. So the point I'm trying to make is that if you have a dynamics, a unitary that takes this form, e to the minus I h, it turns out that it doesn't need to be static. It can be some sort of drive, 0 to t of h of t dt, where this is going to be the time ordered product. If I have a drive with this form, where x to some number, let me not use n, but to some number k is the identity. In our previous case, k was 2. Then you can show that there's a slightly rotated frame that I'll kind of ignore for now, where the dynamics are well approximated by the symmetry that I acted on and some effective Hamiltonian, but now where this effective Hamiltonian commutes with my symmetry. And this is good up to exponentially small, up to exponentially small parameters. Okay. So what I hopefully convince you is by having a drive, I don't just mimic a generic effective Hamiltonian. I can actually use that drive to induce new kinds of symmetries into my system. And because of this structure, those symmetries are ZK symmetries. So a spin flip, a clock, that's kind of the thing that you should think about. Awesome. And now over the next 10 minutes, I'm going to use this kind of ingredients to generate a time crystal, i.e., again, a phenomena that has the subharmonic response, but that it's kind of like different from the MBL time crystal that I presented last time. Okay. So is this kind of construction, does this make sense? Are there any questions? See some approving nods. Are there any dissenting nods? Really? Okay. Okay, so I'm going to need a few more pages, so let me just prepare this at page. Sorry. No, this didn't work. Delete. Sorry, I'm showing a little bit how the sausage gets made. Okay. So how does this come to be? So let's go back to this picture over here, right? And use it as our basis. So I just hopefully convinced you that something cool can happen when you drive your system. But now I went back and I got the previous figure of a static Hamiltonian. And the reason why this is going to be a good starting point is that before analyzing the dynamics every period, U of F, I want to look at the dynamics after every K periods. Okay. And in this case, I basically have that this is X, E, this is approximately equal. Let me be careful about this. H effective T and K times, right? But because X and H effective commute, I can actually bring them all the X's to the front and just do E to the minus H effective KT. And this by fiat that I said at the start should just be the identity. So what I'm saying is that because of the structure of this drive, if I look at my system, not every period, but every kth period, the dynamics are basically capturing the physics of that static Hamiltonian. Okay. And so we can now try to understand the dynamics of my system. So at t equals 0, I'm going to start in some particular initial state. Let me write density matrix just to make the comparison easier. And what I'm saying is that there is some time that I called tau pre before, where my system is effectively going to approach an equilibrium state with respect to this effective Hamiltonian. Let me call that H effective. Okay. And then there's going to be another time scale where my system approaches this infinite temperature state. Okay. So far, so good. But there's one difference between now and before, is the fact that we have this additional symmetry of my system. So there's actually different effective Hamiltonians that I can approach. One of them can be the symmetry respecting Hamiltonian. So let's call that the symmetry respecting. And the other is going to be the spontaneous symmetry broken state. And that is, again, not just because of the properties of my initial state, its energy density and maybe the way that it orients itself, that's going to set which of these states go. The way that you should think about this is in terms of paramagnets and ferromagnets. So imagine that you have an initial, you have a low energy initial state on a system that has some ferromagnetic order, and you let the system evolve. If it's going to equilibrate and it has this ferromagnetic order, it's going to organize itself onto a ferromagnet of one particular direction. And the details of my initial state is going to say if it's going to point down or if it's going to point up. But if I change the energy density in my initial state, eventually it's going to go into the paramagnetic phase. And now this equilibrium state is just going to be a boring paramagnet. So maybe making this, maybe kind of illustrating this, there's kind of an axis that's going to be effectively the energy density of my initial state. And there's going to be some critical point, let's call it HC. And if I prepare a system below, it goes onto one of the spontaneous symmetry breaking states. For example, a ferromagnet pointing down or a ferromagnet pointing up. And if I go above, the symmetry respecting set is effectively going to be unique, and it's kind of like going to be the boring paramagnet. Okay. So that gives us already something distinct and something novel. And now we can use this to realize this periodic doubling, because remember, this picture is only true every k periods. So now we can ask ourselves what happens if we look at the system every period. And nothing's going to truly matter at the start. A lot of things is happening as the system equilibrates. But the important thing is what happens on this very large regime, right? If I have a symmetry respecting state, and I understand its dynamics under my approximate unitary, this is effectively going to be, oh, this should be a dagger, effectively going to be e to the minus I h effective t x rho s r x e to the plus I h t. Let me simplify that for space reasons. And because the symmetry respecting state, this is going to be itself. Right? And because of the thermal state, it goes back to itself. So a system, if I'm in the symmetry respecting state, what's going to happen is that every period, I'm just going to go to the symmetry respecting state again. Okay. But if I'm in this, the symmetry broken phase, what's going to happen is that I'm going to not necessarily write everything, but the crucial aspect is that when I act with this X operator, is effectively going to flip me between the different symmetry sectors. So again, with the analogy of the ferromagnet, I have a ferromagnet pointing up. I do a spin flip, so I still have a ferromagnet, but it's going to be a ferromagnet pointing down. So I can denote that as rho prime SSB. And then I have this evolution under the effective Hamiltonian. But because it's a thermal state, it's going to be unchanged under this. So if I, before going into that, if I grab some additional writing space and maybe make a couple more. The dynamics of my system is going to be different on these two regimes. So if I, in the symmetry respecting state, I start with some initial state. Eventually I get to this tau pre, and this is log t again. And then I look at tau star. And within this regime, every period, the system is going to be in the symmetry respecting state. Okay. But if my initial energy density is low enough, suddenly I'm going to be, I still have some odd dynamics up until my system is going to thermalize. I don't want to make too many comments about that. But once I'm in this prethermal regime, every time I act with a symmetry with my dynamics, I'm going to move to a different symmetry sector up until the kth term, where I effectively have to go back to the initial one because my system has to look static. Okay. And this again is nothing more than this subharmonic response, because even though my dynamics are periodic in time, the system only comes back to itself after k periods. And this allows me to kind of like build what has been coined this prethermal, because it doesn't it's only robust within this prethermal regime, and then discrete time crystal, because I'm fundamentally using the drive to set kind of my translation symmetry of my dynamics, and then breaking that into a bigger case like we saw yesterday. Okay. You should think the way that one way to think about this is I wrote it in terms of energy, but there's kind of like this duality where you can also think in terms of temperature, because the fact that you're approaching a thermal state means that there's a critical temperature. And this is how you think of classical phase transitions. If my system equilibrates with respect to this pre-thermal Hamiltonian, it's going to be given by a Gibbs ensemble of that effective Hamiltonian that has some temperature that is set by the initial energy density of my state. And as I tune that, I'm effectively tuning the temperature of my system, and I can tune it up and down by preparing a hotter or a colder state. That's a very good question. Did it make clear this kind of, I've been using energy and temperature interchangeably, but does that kind of clarify that? Awesome. So hopefully I convinced you that I gave you the mental framework of why this should happen. So now let me kind of show you some data. So these are kind of numerics on large, I think it's 24 spin systems. And what we're effectively doing is exactly what I told you. We have some Hamiltonian that has, in this case, some long-range interaction. It's in 1D, and that's why I need long-range interaction. And then I effectively, I don't need to point, I can just like use this. And then I effectively apply a global pi pulse that's rotating all the spins. Now, in general, as you can see, I have this effective field, and this effective field doesn't commute with my spin flip. So a priori, my system has no symmetries. The only symmetry it has is time translation symmetry. And then I just run the numerics through my system. And I keep track of 3 quantities, 2 that are already introduced, this effective energy density and entanglement entropy. And these are good sanity checks. We see the same features as I told you before, in that it takes a very long time for my energy density to change. And eventually, as I change the frequency of my drive by units, that the time scale changes by orders of magnitude. So that is indeed capturing this exponentially slow heating. And that feature, while the overall factors depend on the initial state and whatnot, the scaling does not. And even if you prepare a completely different state that has a much lower, it's a much hotter state, you actually see that the system exhibits the same scaling. We can also see that the dynamics of this pre-thermal plateau is also there. We see that the system has some pre-thermalization timescale, after which the entanglement kind of gets stuck, which corresponds to the system approaching this this thermal state of this pre-thermal Hamiltonian or effective Hamiltonian. And again, that feature is independent of the initial state that I consider, even though some aspects of the particular thermalization times might depend. The crucial distinction is the bottom plot, right? So in the bottom plot, I'm keeping track of effectively an order parameter of this time crystalline order. And I'm kind of like differentiating between the dynamics under even periods and under odd periods. And on the left, what we see is that the system basically kind of ping-pongs back and forth between even and odd periods, between a positive magnetization and a negative magnetization. And crucially, it plateaus, and the way it starts decaying is around the same time as the thermalization timescale of my system. So indeed, we understand this as, again, our system having some pre-thermal equilibration dynamics. And then there's an exponentially large region where its system lives on this robust time crystalline phase before the drive starts heating up the system and I go into fully mixed state. And this by itself, you might, but how is that specific to this? What's the features? Turns out that if you sweep the initial state, as long as it's below the critical temperature of the state, you see features like this, where the order parameter is kind of like captured by the equilibrium magnetization, by the magnetization of the equilibrium state of the spontaneous symmetry broken phase. Crucially, if you take exactly the same dynamics, but you change the initial energy scale, for example, by tuning the size of this domain wall, you get the dynamics that are completely different. And what we see is that regardless of the frequency, all of this magnetization dies within the same time scale. And that decay is actually captured by the dynamics under just the effective Hamiltonian. And that's this black line that I'm commenting. So this black line is what happens if I do the dynamics just under this effective Hamiltonian. So awesome. So it works. We can do numerics and we can see it. It turns out that you can also see an experiment. The reason why we chose this Hamiltonian is that these long-range interactions are kind of the long-range interactions that naturally arise in an ion trap system, where basically the qubit that is encoded within each ion interfaces with emotional modes to generate long-range interactions that have some particular spatial structure that mimics a power law. And crucially, in these systems, these native interactions implement these Ising couplings that allow us to have this spontaneous symmetry broken phase. And then you can use kind of gates to kind of like rotate the system and do the simulation of these dynamics. And what you see is that it's kind of like encoded here, which is if you start with a hot state above the critical temperature, you have that regardless of the frequency of your drive, eventually everything decays on a time scale that is independent of frequency. But if you choose a low enough energy density state, you see a robust period doubling up until some time scale in which the system heats up. Now, for a careful looker, you probably notice that I no longer log the time plot, the time of these. So one aspect that is important to note is that this exponentially long thermalization timescale depends on the fact that your system is isolated. So the moment you actually run an experiment where, in this case, you have laser noise, the laser noise fundamentally breaks our assumptions, in particular breaks the time translation symmetry, and adds additional sources of decay. And that's why the heating in an experiment is always limited by those factors. And that's why you don't see exactly an exponential scaling, but you still see a very strong enhancement of the thermalization timescale. And because, similar to what Christian alluded, the fact that you can take a snapshot of the entire experiment means that you have these very pretty plots where you can see the dynamics of the entire system and see kind of the propagation and the decay of the magnetization across the entire system. Awesome. So I think I'm running a little bit out of time. Let me just comment that it seems like everything that you can get is related to like symmetry breaking. It's going to be some maybe flipping of the symmetry breaking sectors. Turns out that you can do more complicated and kind of exotic stuff. I'll just kind of flash some pictures and I'll invite you to ask me stuff about this. Turns out that you can, if the effective Hamiltonian has some topological order, you can do this time crystalline response not in local observables, but actually in kind of like the logical operators that Harry was telling us about yesterday. On the other hand, some topological phenomena, not topological order, but within the context of these SPTs, can actually host corner modes. And because they're localized, you can actually use different ways of kind of different kinds of protocols for kind of like preventing their thermalization. So one thing that I now realize why I had this blank page is that I wanted to compare this pre-thermal time crystal with the MBL time crystal that I talked about yesterday. So just to kind of like emphasize that point. And it's going to be kind of quick, but I just want to kind of allude that these are kind of slightly different, even though the signature of them is the same. It's like this period doubling phenomena. I want to kind of emphasize some distinctions that helps us kind of put this time crystalline phenomenology in different regimes. So one thing that we call it DTC. So one thing that was a point of discussion yesterday, and kind of like it's important to emphasize, is kind of the notion of the lifetime of these phenomena. What I told you today is that these only work as long as the system is in this pre-thermal regime. So we know that the lifetime of these phenomena fundamentally are limited by the frequency of the drive and the coupling of our system. So there is a finite yet albeit very long time scale for my system. In these MBL DTCs, in principle, and based on yesterday's comment, let's put a little asterisk over here. These timescales could be infinite, or at least like exponentially controlled in the disorder strength of your system. Okay? The other important point is the notion of initial state. So for the MBL, I emphasize that this time crystalline phenomenon could be understood by this pi pairing across the entire eigenspectrum of the system, which means that no matter what your initial state, you should see some subharmonic response. On the other hand, this pre-thermal time crystal only worked if the initial state thermalize to a spontaneous symmetry breaking phase of my effective Hamiltonian. So this tells us that we need the kind of the temperature of my initial state, or the corresponding temperature, to be below some critical temperature. So that tells us that in fact there has to be some more important initial state dependence. I think an important point that's I like emphasizing is disorder. So the reason why MBL comes to be is the fact that you use these strong levels of disorder to kind of like suppress thermalization. But all the physics that I told you were in very generic features of Hamiltonian. So actually you don't need disorder. You can work and see this kind of phenomenology in clean translational invariant systems. And finally, there's this notion of interaction range. And let me also call them interaction range / dimensionality, where MBL fundamentally, because you need this localization, you're limited to 1D short range systems. Again, little asterisk. So it's kind of 1D short range. Whereas the story about prethermalization actually we saw carried over even in the case of long range interactions, and it was completely agnostic of the dimensionality. So as long as your system, you can have interactions that allow you to have a symmetry broken phase, you basically can get the phenomenology of this discrete time crystal. So I think it's been an hour, is that correct? Okay, so my next lecture is going to be on something completely different. So I'm going to request the chair for 10 more minutes to give you a little bit of a feeling of hydrodynamics. The chair nods in approval. Okay. So, okay, so before jumping into a completely different story, are there questions? Yeah. No, this is assuming I'm assuming that the system is isolated and I can treat it as a spin system. Those I would interpret as effectively noise. It's kind of like giving kicks and coupling my spin degrees of freedom to my motional modes. You might have. These considerations are quite generic. So one in general then has to think of like the properties of the kinetic energy and whatnot. One thing to note, and maybe this connects a little bit, is that these statements work when your Hilbert space is bounded. The moment you have bosons and things moving around, you need to be somewhat careful. And intuition is like, there's one, if you have, for example, a particle that can have infinite kinetic energy, there's one local rearrangement that allows you to absorb as much energy as this, which is you just eject the particle very fast. So this is why you need a bounded Hilbert space to get some of these features. So in bosonic systems, these thermalization bounds are actually polynomial rather than exponential. That's a good question. I think it was like, I don't remember. I think it was like 1.3 or 1.13. But yeah. But it turns out that sorry? Yeah, it turns out that if you go into, one reason why you don't want to go into the Coulomb regime is that this notion of local energy scale breaks down, because then you have log corrections. And if you go below, you break this, you no longer have this local energy scale, and actually things kind of break down because of it. So as you increase your system size, your thermalization rate changes. And I actually have some plots on a different paper that show that if you normalize by this local energy scale, everything works out, but you need to be careful about how you define this local energy scale. Yeah, it changes because it changes this local energy scale, but the scaling wise, it shouldn't change. Yeah. Awesome. Okay. So I think I don't want to necessarily make Christian wait too long for his second lecture. So I want to give kind of like an overview of like not how dynamics out of equilibrium can be different in isolated quantum systems, but actually how we approach the equilibrium in these isolated quantities can have very interesting phenomena. And I'll kind of like run this kind of quickly, which is kind of motivating through the lens of hydrodynamics. So in hydrodynamics, we know that Navier-Stokes is kind of successful. We build airplanes and we understand sonic booms. So we know that fundamentally we have emergent descriptions of fluids that are very effective and very accurate. And instead of taking care of the 10 to the 24 particles, we know that we can cook up like fields of, in this case, velocities, pressures, and even forces that allows us to understand the entire dynamic of the system. And the universal properties of the late time near equilibrium dynamics are encoded on these equations, right? And fundamentally, the way that these ideas come to be is that you still underlie a notion of equilibrium, but at smaller length scales. So you have a very big system, the size of your plane, but you assume that there's kind of like a smaller length scale, let's call it a cell length scale, on which the system is at some notion of local equilibrium. And that allows you to talk about the velocity of this particular cell, for example, right? And by thinking of how the velocity of this cell interfaces with the velocity of the nearby cells, allows you to build hydrodynamical descriptions that are often constrained by properties of the system, such as symmetries. Okay, so Navier-Stokes and hydrodynamics is very complicated for me. So let me kind of give you a simple example in terms of spin diffusion, right? So imagine that you have a system with a conserved magnetization, and you want to, it's kind of some sort of M of X, right? And you know that if your system is local and has a conserved magnetization, the magnetization on this cell can only go to its neighboring cells through some form of current. So you end up with this property that the time dependence of this magnetization is related to the divergence of the currents. And this sets exactly how the magnetization of your system changes. Now, in principle, we rewrote the problem encoding this notion of conserved quantities, but then in principle, you can just, assuming a long wavelength approach, you can just write this currents as kind of properties of, as kind of like a series expansion on the long wavelength features. And to lowest order, you always expect this to be proportional to the gradient of magnetization. If I have marked magnetization on the left and on the right, things are going to move from the left to the right, and that's going to be the current. And this allows you to derive an expression which is for the, let me put a D here for the diffusion coefficient. And this just tells you that on very general grounds, you expect that a single conserved quantity is going to diffuse in your system. And the fact that we only use the notions of local equilibration, the symmetries, i.e. the conservation rules, and the fact that we only had to care about one conserved quantity is what allows us to get so quickly such an effective hydrodynamic description. And in principle, the actual details of the system don't matter. My coupling strength is slightly different. If my scattering constant between my particles is different, it should come into D and the strength, the numerical values, but not change the shape of this equation of motion and thus the universal properties of my system. And it turns out that AMO systems kind of told us that things get more interesting once you have more conserved quantities. And I think historically that is known because of this experiment, on which they basically take two gases, put them on a trap, and just let them go. And what happens is that they basically seem like they hit one another and go back, or go through one another. So they call this the Newton cradle experiment because it looks like the little like desk toy. But the crucial aspect of it is like, it's not that these particles are not equilibrating. If you look at properties of like distribution of momentum and rapidity, they kind of look thermal. It's not like a thermal ensemble, but it's a thermal set of expectations. And that kind of tells us that the presence of additional conserved quantities, in this case, you have a Lieb-Liniger model, and that's where you have conservation, can lead to hydrodynamic-like phenomena that is very different from what you'd expect from just having a single conserved quantity. Okay? So there's kind of because of this, because of these observations, people are now being very interested in studying the dynamics and the phenomenology of integrable models. And let me kind of emphasize this point. I'm defining an integrable model as kind of a model with an extensive number of local conserved quantities. So the simplest example that you probably know is free fermions. So you have free fermions that hop on a lattice, and it can go from left to right. And you know that the occupation of each fermion is a conserved quantity. So that gives us an integrable one. I don't like thinking about fermions, so let me map it onto a spin problem. It turns out that this problem exactly maps into an XY model where I have spins in the lattice that are basically interacting with these kinds of interactions. Okay? And it turns out that if you look at this model, it displays a notion of ballistic transport. Even though you have a conserved quantity in the total magnetization, U1 total magnetization, U1 symmetry, the total magnetization is conserved. If you look at the propagation of spin in the system, it looks ballistic. And the intuition in terms of free fermions is very clear, right? Each fermion has a little bit of magnetization. You populate some here, and because they're free, they just move around at some velocity, and they show up on the other side in some ballistic fashion. It turns out one reason why this model is kind of cool is that you can actually add kind of ZZ interactions. And even though it makes this model no longer free fermions, it actually adds interactions that change the character of our system. And as I told you, there's kind of like, okay, yeah. There's kind of this landscape on which if you look at transport as a function of this delta, nearest value of 0 is going to look ballistic. However, if you look at very large delta, now your model still has local integrals of motion, but it's no longer these free fermions that carry magnetization. The excitations you should think are effectively domain walls. Delta is going to be very big, so that's going to set your like your preferred basis. And you should think that if you have one spin up and one spin down, they really don't want to break away because that has a large energetic cost. And fundamentally, a domain wall can never carry spin, right? If you have kind of like this bounded object, and even though it might move ballistically, it may not carry any particles because it's a combination of up and down spins. Okay? But one thing that can happen is that these objects, so you might worry that there's no transport because domain walls are going to be fixed. It turns out that if you're thinking at infinite temperature, these domain walls can interact with other domain walls and jiggle them around. The easiest ways to understand is through this picture. So what I'm looking here is kind of like a domain wall that is kind of approaching a much bigger domain, which is kind of like this particular branch. So on this side of the system, it looks like I have a spin down that's moving through a sea of spin ups and is carrying some magnetization. But actually, when it hits this domain wall, it actually is able to just move through. I'm never changing the number of domain walls. So for example, here, there's one over here and one over here. So there's 3. Over here, there's still 3. And over here, there's still 3. Right? But what happened was twofold, is that now instead of moving a spin up down in a sea of spin ups, I'm moving a spin up in a sea of spin downs. So even though these particles are moving ballistically, if I average over the entire system, I'm actually not carrying any magnetization ballistically. But what I'm doing is I've effectively shifted the location of this domain wall by a little bit. So one way that you should think about this is that in this limit of very large delta, where the domain wall is the right basis to think about the dynamics, what you have is that ballistically, domain walls are moving, but they're not carrying magnetization. But as they interact with other bigger domain walls, they're moving them around in some sort of like random walk. At some point, some particles are going to come from the left. At some point, it's going to come from the right. And these domain walls are effectively going to diffuse. And so what we expect is that in this regime, instead of ballistic transport, we should actually have a diffusive transport. Okay. So this is kind of interesting because all I did was tune one particular parameter of my system. I didn't change the symmetries of my model. I didn't change the dimensionality. I didn't change the range of interactions. But suddenly I have two very different phenomena. And that has to do with the fact that this system has this integrability that induces a lot of conserved quantities in the background. Okay. So I'm trying to gauge exactly how much. Okay. Yeah. So I will not say why, but it turns out that if you look at the particular point where delta becomes 1, and this model becomes spin rotation symmetry, gains an SU2 symmetry, the system is neither ballistic nor diffusive, but it's actually what is known as super diffusive. It's unlike Superman, is not a better form of diffusion. It's just something a little bit faster than diffusion. And we can quantify this, and let me jump onto this plot. And the way that you can do it is you can effectively prepare a small spin imbalance, and you can see how much spin goes from the left side of this imbalance to the right side of this imbalance. And you can quantify this in the way that it scales with time. And if I have a ballistic system, there's going to be particles over here on the left side of my system. And as they move ballistically to the right, and that effectively is going to capture what is the universality class of our system. And if z equals 2, it's diffusive. If z equals 1, it's ballistic. If z equals 3 has in this intermediate regime that it's super diffusive. And the point that it turns out is that this is a generic property of integrable systems with non-abelian symmetries. And one thing that we've conducted is to show that this is quite generic. So you can make this statement more precise and look not just at the polarization transfer, but actually look at the 2-point correlation function of these transport dynamics. And what you see is that regardless of the symmetry of our model, you're kind of just labeled by the symmetry group, you see that the system exhibits a scaling collapse with one another. They all fall under the same universality class. And that universality class at the level of these 2-point correlation functions agrees with this kind of like black line, which is capturing the Carter-Parisi-Chang universality class. So that universality class is what sets like the growth of fires, the growth of like surfaces. When you have like ice melting on your windshield, the pattern and the universality properties of that pattern are captured by this Carter-Parisi-Chang. And here it kind of emerges, or kind of like at this particular level of terms, it emerges at correlation function, it emerges on the deterministic dynamics of magnetization. And indeed, these models that you can do, this kind of this Heisenberg model over here, you can actually do it in an experiment. So people have looked into this in kind of two settings. One is in the context of optical lattices. So basically, they're able to build a standing wave of light, put atoms, and basically, as Harry told us, use the internal degree of freedom to kind of like determine the state of the system. And if you fill this optical lattice at unit filling, you actually have that the emergent dynamic is going to be a Heisenberg model. If you kind of constrain them to only talk to each other along the horizontal line, you have a 1D Heisenberg model, which is exactly the model that I told you should have this super diffusive behavior. And when they prepare exactly this dynamics, they see indeed that particles move back and forth. And they can see that the dynamics are neither ballistic nor diffusive, but have this kind of like 2/3 scaling characteristic of this super diffusion. The interesting thing, and I think why, and I want to kind of like emphasize this point, experiments now can probe things that we can't. When they take a picture, they have a snapshot not only of the polarization, but actually of much higher moments and much more subtle features of this process. And you can actually start using this to try to ascertain features that in numerics we cannot see. So in the left plot, in this plot, what they looked at was exactly look at higher moments of this distribution as a way of understanding other features of this universality class. And indeed, this is something that more recently was conducted in using Google's experiment. And there they basically implemented the same kind of experiment. And they saw that if you look at later times and with weaker size of this domain wall, you actually get a slightly different value of some of these skewnesses of these probability distributions. And all this is to say is that at present, like took 3 years to refine these kinds of experiments. But what they found is that even though in these 2-point correlation functions, this universality class looks like this KPZ, it seems like the dynamics is fundamentally different from it. So I want to kind of use that to kind of like jump off to some concluding remarks, which is like the fact that we have access to these machines is enabling us to study very different phenomena that in principle are very difficult to study in the solid state one knot. We don't have other platforms for studying these isolated dynamics, and there's kind of a wealth of phenomena to be studied, a wealth of dynamical regimes to investigate. And I think this is kind of a good example where as theorists are used to being able to compute things for AMO experiments and then having guide what is the observations, we're now approaching the regime where, whether it is in the optical lattice that Christian mentioned or on these dynamical experiments, we can actually use these machines to investigate fundamentally novel phenomena and get new insights into the nature of possible dynamics. And this is all in the context, all that I talked in the past 2 lectures in the context of isolated quantum systems. What we've learned, for example, from Harry is that if we measure and we learned about the system, we can have even more particular, we can control the dynamics and can learn more about the quantum state. So I think this kind of like what excites me about this field and why I wanted to talk a little bit about this is that I think that these are kind of directions that allows us to investigate phenomena we never thought of before, and hopefully kind of like uncover other, like an entire landscape and kind of like new sets of universality classes, the same way that we think of that way for phases of matter. So I wanted to end a little bit on my soapbox on this lecture, because next lecture I'll talk about quantum sensing and how quantum computers will help, which is not entirely, but probably almost completely in like what I talked about today. So I just want to finish on some notes. And I also built some references, and I'll share the slides if you send me an email, or I'll coordinate with Jose.
I think Jacqueline should have actually created
A folder. Perfect. Awesome.
Thank you. Francisco is around. And Boyd, maybe I'll make a remark. I got a text from Kim that those who are interested about the